To determine the correct size of the grounding electrode conductor, or GEC, for a 4000 amp 120/208 volts, 3-phase service with 10 sets of 500 kcm conductors from the power company to the 4000 amp main service disconnect switch, we need to follow a specific process outlined in the National Electrical Code, or NEC. This process involves several steps, focusing on the ampacity of the conductors and the relevant NEC tables. Firstly, identify the largest conductor. The largest conductor from the power company to the main service disconnect switch is 500 kcm. Secondly, determine the ampacity of the phase conductors. The service amperage is 4000 amps. Since this is a 3-phase service, the current is distributed across 3 phases. Although the total service is 4000 amps, you will use that figure in calculations later and do not divide it here. Now, determine the grounding electrode conductor, or GEC, size. According to Table 250.122 of the NEC for service ampacity of 4000 amps and a conductor ampacity that we will calculate, the GEC must be sized according to the calculation outlined. Let's look at the calculation. The GEC size is equal to the service ampacity divided by 10, multiplied by the largest conductor ampacity divided by the phase conductor ampacity. GEC size equals 4000 divided by 10, multiplied by 1333.33 divided by 1333.33. GEC size equals 400 kcm. Therefore, the correct size of the grounding electrode conductor is 400 kcm. The NEC Table 250.122 provides the minimum size requirements for grounding electrode conductors based on the size of the service entrance conductors. The table specifies the copper or aluminum conductor size required for various service entrance conductor sizes. It's crucial to consult this table directly in the NEC handbook to ensure accurate sizing, as interpretations can sometimes vary and the code is updated periodically. Grounding electrode conductors connect the service equipment to the grounding electrode system. The grounding electrode system typically consists of items like ground rods, metallic water pipes, or concrete encased electrodes, often referred to as UFA grounds. These electrodes provide a low impedance path to earth, which helps to stabilize voltage to earth during normal operation and provides a path for fault current during ground faults. The size of the grounding electrode conductor is crucial for safety and proper operation of the electrical system. An undersized GEC can lead to elevated ground potentials during fault conditions, increasing the risk of electric shock and equipment damage. An oversized GEC, while not necessarily harmful, can be more expensive than necessary. Selecting the correct size ensures that the grounding system can effectively carry fault currents back to the source, allowing overcurrent protective devices like circuit breakers or fuses to operate and clear the fault. It's important to note that the calculation method provided is a simplified representation. The NEC contains detailed requirements and exceptions that may apply to specific situations. For example, if the service consists of multiple sets of conductors, the equivalent size of the conductors must be determined before applying Table 250.122. Additionally, the type of grounding electrode used can influence the required size of the GEC. For example, a concrete encased electrode may have different sizing requirements than a ground rod. When installing grounding electrode conductors, it's important to follow all applicable NEC requirements for installation methods. The GEC must be installed in a manner that protects it from physical damage and ensures its long-term reliability. This may involve running the GEC in conduit or using other protective measures. The GEC must also be connected to the grounding electrode system in a manner that provides a reliable low-impedance connection. This typically involves using approved connectors and methods such as exothermic welding or listed grounding clamps. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. Grounding connections should be checked periodically for corrosion or damage, and any necessary repairs should be made promptly. Grounding electrodes should also be tested periodically to ensure that they maintain a low resistance to earth. High resistance can indicate a problem with the grounding electrode system, such as corrosion or a broken connection. In summary, determining the correct size of the grounding electrode conductor for a 4000 amp service requires careful consideration of the NEC requirements, including Table 250.122 and other relevant sections. The calculation method provides a starting point, but it's essential to consult the NEC directly and consider any specific factors that may apply to the installation. Proper installation and maintenance of the grounding system are also crucial for ensuring its long-term reliability and effectiveness. Always consult with a qualified electrical engineer or inspector to ensure that the grounding system meets all applicable requirements. The grounding electrode conductor plays a critical role in the safety and proper operation of the electrical system, and it's essential to get it right. The grounding system ensures safety by providing a low impedance path for fault currents, which helps to protect people and equipment from electrical shock and damage. It also helps to stabilize voltage to earth, which can improve the performance of sensitive electronic equipment. A properly designed and installed grounding system is an essential component of any electrical system. To recap, the calculation mentioned previously is a simplified representation, and the NEC should always be consulted for specific requirements and exceptions. Here is a more detailed explanation, and remember to always consult the NEC book. We have to determine the size of the grounding electrode conductor for a 4000 amp service, supplied by 10 sets of 500 kc mil conductors, operating at 120/208 volts, 3-phase. This requires a careful application of the National Electrical Code, NEC, specifically Article 250, which covers grounding and bonding. Firstly, the service entrance conductors are 10 sets of 500 kc mil copper conductors. We need to determine the equivalent size of these conductors to use NEC Table 250.122. Since we have 10 parallel conductors per phase, we can consider the total ampacity that these conductors must carry. However, for sizing the grounding electrode conductor, we focus on the size of a single conductor set. Therefore, we will use the 500 kc mil conductor size as the basis for our calculation. Secondly, we reference NEC Table 250.122. This table provides the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. The table lists conductor sizes and corresponding grounding electrode conductor sizes for both copper and aluminum conductors. For copper service entrance conductors, Table 250.122 indicates the minimum size of the grounding electrode conductor. We need to find the row in the table that corresponds to a 500 kc mil copper conductor. According to Table 250.122, a 500 kc mil copper service entrance conductor requires a minimum number 1/0 AWG copper grounding electrode conductor. However, this is a simplified interpretation because we need to also consult other factors. Thirdly, grounding electrode conductor material. The grounding electrode conductor can be made of copper, aluminum, or copper-clad aluminum. The choice of material affects the size of the conductor required. Copper is a more conductive material than aluminum, so a smaller copper conductor can carry the same amount of current as a larger aluminum conductor. In this case, we are assuming that the grounding electrode conductor is made of copper. Aluminum grounding electrode conductors must be sized according to Table 250.122, using the aluminum conductor column. Fourthly, grounding electrode type. The type of grounding electrode also affects the size of the grounding electrode conductor. The NEC recognizes several types of grounding electrodes, including ground rods, metallic water pipes, concrete encased electrodes or EU for grounds, and ground rings. Each type of grounding electrode has its own requirements for size and installation. If a ground rod is used as the grounding electrode, the grounding electrode conductor must be at least number 6 AWG copper or number 4 AWG aluminum. However, this requirement applies only to the connection to the ground rod itself, and the overall size of the grounding electrode conductor must still be determined by Table 250.122. If a metallic water pipe is used as the grounding electrode conductor must be sized according to Table 250.122, but it must also meet certain requirements for bonding and continuity. The water pipe must be bonded to the service equipment enclosure and to any interior metallic water piping systems. If a concrete encased electrode is used, the grounding electrode conductor must be at least number 4 AWG copper. The concrete encased electrode must be at least 20 feet long and must be encased in at least 2 inches of concrete. Fifthly, multiple grounding electrodes. If multiple grounding electrodes are used, the grounding electrode conductor must be sized to connect all of the electrodes together. The size of the grounding electrode conductor must be based on the largest service entrance conductor, as determined by Table 250.122. In this case, since we have 10 sets of 500 kcmil conductors, we would use the 500 kcmil conductor size as the basis for our calculation. However, we must also ensure that the grounding electrode conductor is large enough to carry the fault current from all of the electrodes. Sixthly, we will look at continuous grounding electrode conductor. The grounding electrode conductor must be continuous from the service equipment to the grounding electrode. Splices are not permitted in the grounding electrode conductor unless they are made using irreversible compression connectors or exothermic welding. The grounding electrode conductor must be protected from physical damage and must be securely fastened to the service equipment and to the grounding electrode. Seventhly, we will look at the available fault current. The available fault current at the service equipment must be considered when sizing the grounding electrode conductor. The grounding electrode conductor must be large enough to safely carry the available fault current without overheating or melting. The available fault current can be calculated using engineering methods, or it can be obtained from the local utility company. Eighthly, local amendments. Local jurisdictions may have amendments to the NEC that affect the sizing of grounding electrode conductors. It is important to check with the local electrical inspector to determine if there are any local amendments that apply to the installation. Ninthly, specific example calculation. Assuming that we are using copper conductors and a ground rod as the grounding electrode, the minimum size of the grounding electrode conductor would be number 6 AWG copper for the connection to the ground rod. However, the overall size of the grounding electrode conductor must still be determined by Table 250.122, which would require a minimum of number 1/0 AWG copper for a 500 kcmil service entrance conductor. The number 1/0 AWG copper conductor would be run from the service equipment to the ground rod, and it would be connected to the ground rod using a listed grounding clamp. Tenthly, professional consultation. It is always recommended to consult with a qualified electrical engineer or inspector when sizing grounding electrode conductors. Grounding systems can be complex, and it is important to ensure that the system is properly designed and installed to meet all applicable requirements. A qualified professional can help to ensure that the grounding system is safe and effective. In summary, determining the correct size of the grounding electrode conductor for a 4000 amp service requires a careful application of the National Electrical Code, specifically Article 250 and Table 250.122. The size of the grounding electrode conductor depends on the size of the service entrance conductors, the material of the grounding electrode conductor, the type of grounding electrode, the number of grounding electrodes, the continuity of the grounding electrode conductor, the available fault current, and any local amendments. It is always recommended to consult with a qualified electrical engineer or inspector when sizing grounding electrode conductors. So to summarize, we will go through it once again. We need to calculate the grounding electrode conductor, or GEC, size for a 4000 amp service. Step 1 is to determine the service entrance conductor size. The service is supplied by 10 sets of 500 kcmil copper conductors. Although there are multiple conductors, we base our GEC sizing on the size of a single set, which is 500 kcmil copper. Step 2 is to consult NEC Table 250.122. This table provides the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. Find the RA corresponding to 500 kcmil copper conductors. Step 3 is to read the table. According to NEC Table 250.122, A 500 kcmil copper service entrance conductor requires a minimum number 1/0 AWG copper grounding electrode conductor. Step 4 is to consider other factors. Review other requirements in NEC Article 250, such as those related to the type of grounding electrode, the material of the GEC, and any local amendments. Step 5 is to verify your calculation. Ensure that the selected GEC size meets all applicable requirements and is sufficient for the available fault current. Step 6 is to consult a professional. It is always recommended to consult with a qualified electrical engineer or inspector to ensure that the grounding system is properly designed and installed. Based on NEC Table 250.122, the minimum size of the grounding electrode conductor for a 4000 amp service with 500 kcmil copper service entrance conductors is number 1/0 AWG copper. It is important to consult the latest edition of the NEC and to verify all requirements with a qualified electrical engineer or inspector. Also note that the table is a minimum and the number 1/0 AWG is a minimum number based on what we were able to see from the table. Now let's talk about some other grounding concepts. Grounding is a critical aspect of electrical safety, and there are several related concepts that are important to understand. These concepts include bonding, equipment grounding, system grounding, and ground fault protection. Bonding refers to the practice of connecting together all metallic parts of an electrical system to create a low impedance path for fault current. Bonding helps to ensure that all metallic parts are at the same potential, which reduces the risk of electric shock. Bonding is typically achieved by using bonding jumpers, which are short lengths of wire that connect together metallic parts such as conduit, enclosures, and equipment frames. Equipment grounding refers to the practice of connecting the non-current carrying metallic parts of electrical equipment to the grounding system. Equipment grounding provides a path for fault current to flow back to the source, which allows overcurrent protective devices to operate and clear the fault. Equipment grounding is typically achieved by using equipment grounding conductors, which are wires that connect the equipment to the grounding system. System grounding refers to the practice of connecting the neutral point of an electrical system to ground. System grounding helps to stabilize voltage to ground and provides a path for fault current to flow back to the source. System grounding is typically achieved by using a grounding electrode conductor, which connects the neutral point of the system to a grounding electrode. Ground fault protection refers to the use of devices that detect ground faults and automatically disconnect the power supply. Ground fault protection is typically used in electrical systems that serve wet or hazardous locations, where the risk of electric shock is higher. Ground fault protection is typically achieved by using ground fault circuit interrupters, or GFCIs, which are devices that detect small amounts of current leakage to ground and automatically trip the circuit. In addition to these concepts, it is also important to understand the different types of grounding electrodes that are used in electrical systems. The NEC recognizes several types of grounding electrodes, including ground rods, metallic water pipes, concrete encased electrodes, and ground rings. Ground rods are typically made of copper or copper-clad steel and are driven into the ground. Metallic water pipes are used as grounding electrodes when they are in direct contact with the earth for at least 10 feet. Concrete encased electrodes are made of at least 20 feet of number 4 AWG copper conductor that is encased in at least 2 inches of concrete. Ground rings are made of at least 20 feet of number 2 AWG copper conductor that is buried in a ring around a building. Each type of grounding electrode has its own advantages and disadvantages, and the choice of grounding electrode depends on the specific application and the soil conditions. It is important to select a grounding electrode that is appropriate for the application and that meets all applicable requirements of the NEC. In summary, grounding is a critical aspect of electrical safety, and there are several related concepts that are important to understand. These concepts include bonding, equipment grounding, system grounding, ground fault protection, and grounding electrodes. A properly designed and installed grounding system is essential for protecting people and equipment from electrical shock and damage. We should remember that grounding systems are more than just a single wire or electrode. They encompass a network of interconnected components working together to ensure safety and reliability. Here are some additional details to consider about the different components of a grounding system. Firstly, the main bonding jumper. This is a conductor that connects the service equipment enclosure to the grounded conductor, typically the neutral of the electrical system within the service equipment. The main bonding jumper ensures that the enclosure is at the same potential as the grounded conductor, which minimizes voltage differences and reduces the risk of electric shock. Secondly, equipment grounding conductors. These conductors provide a low impedance path for fault current to flow back to the source, allowing overcurrent protective devices to operate quickly and clear the fault. Equipment grounding conductors can be wires, raceways, or other approved conductive paths. Thirdly, bonding jumpers. These short conductors connect metallic parts of the electrical system together to ensure that they are at the same potential. Bonding jumpers are used to bond together conduit, enclosures, equipment frames, and other metallic parts. Fourthly, grounding electrode conductors. These conductors connect the service equipment to the grounding electrode system. Grounding electrode conductors must be sized according to the NEC and must be protected from physical damage. Fifthly, grounding electrodes. These are conductive objects that are buried in the earth and provide a connection to ground. Grounding electrodes can be ground rods, metallic water pipes, concrete encased electrodes, or ground rings. Sixthly, surge protection devices. Surge protection devices, or SPDs, protect electrical equipment from voltage surges caused by lightning or other events. SPD are typically connected to the grounding system and divert surge current to ground. Now let's talk about some common grounding mistakes to avoid. Improper grounding can lead to serious safety hazards and equipment damage. Here are some common grounding mistakes to avoid. Firstly, using undersized grounding conductors. Grounding conductors must be sized according to the NEC to ensure that they can safely carry fault current. Using undersized grounding conductors can result in elevated ground potentials and increased risk of electric shock. Secondly, failing to bond metallic parts. All metallic parts of the electrical system must be bonded together to ensure that they are at the same potential. Failing to bond metallic parts can result in voltage differences and increased risk of electric shock. Thirdly, using improper grounding electrodes. The NEC specifies the types of grounding electrodes that are permitted for use in electrical systems. Using improper grounding electrodes can result in inadequate grounding and increased risk of electric shock. Fourthly, neglecting to protect grounding conductors from physical damage. Grounding conductors must be protected from physical damage to ensure that they remain effective. Neglecting to protect grounding conductors can result in damaged conductors and increased risk of electric shock. Fifthly, failing to maintain the grounding system. Grounding systems should be inspected and tested periodically to ensure that they are functioning properly. Failing to maintain the grounding system can result in corrosion, loose connections, and other problems that can compromise the effectiveness of the system. The NEC is a comprehensive set of rules and regulations that govern the design, installation, and maintenance of electrical systems. The NEC is updated every 3 years to reflect changes in technology and best practices. It is essential for electrical professionals to stay up to date on the latest edition of the NEC to ensure that they are following the most current requirements. The NEC covers a wide range of topics related to electrical safety, including grounding, wiring methods, overcurrent protection, and equipment installation. The NEC is organized into chapters, articles, and sections, each of which covers a specific topic. It is important to understand the structure of the NEC to be able to quickly find the information that you need. The NEC is not a textbook or a design manual. It is a set of minimum requirements that are intended to protect people and property from electrical hazards. It is important to go beyond the minimum requirements of the NEC and to use good engineering practices to design and install electrical systems that are safe, reliable, and efficient. In addition to the NEC, there are other codes and standards that may apply to electrical installations. These codes and standards may be developed by organizations such as the Institute of Electrical and Electronics Engineers, or IEE, the National Fire Protection Association, or NFPA, and underwriters' laboratories, or all. It is important to be aware of all applicable codes and standards and to follow them when designing and installing electrical systems. By following the NEC and other applicable codes and standards, electrical professionals can help to ensure that electrical systems are safe and reliable.